Hello everyone, this is Suresh Kothari. Welcome to segment 6 of my talk. Algebra provides us a compact representation of execution behaviors. It also gives us homomorphisms as a powerful technique. We have illustrated compact representations of execution behaviors and the use of algebraic homomorphisms to verify properties of software for all execution behaviors without enumerating them. We will now illustrate another surprising use of algebra. The algebra in this segment takes us beyond the last 50 years of beliefs and dogmas about structured versus unstructured programming. The insights from algebra are surprising and have important practical implications. In an earlier segment, we observed that CRS has repetitions of successor elements only when the programs have loops with return or break. That raised the question whether repetitions in CRS are related to unstructuredness of programs. We will address that question. In the beginning, structured programming required program segments with only one entry and one exit. For example, Harlan Mills characterizes structured programs can be organized into trees of program segments such that each segment is at most of some prescribed size and with entry only at the top and exit at the bottom of this segment. Structured programming in modern programming languages amounts to regulating the use of gotos by providing control blocks with only one entry but possibly multiple exits. When we refer to programs as unstructured programs, we mean C programs with goto, each of which creates more than one entry in a control block. A goto that creates more than one entry in a loop makes the control flow graph irreducible. The slang spaghetti code is sometimes used to refer to such programs. Before we get into algebra, let's review a few things from a Knuth's paper. The paper has an interesting title, Structured Programming with Goto Statements. On page 282, Knuth gives an example of a goto that creates more than one entry into a loop. He advocates new morality to accept such goto statements in certain situations. Knuth quotes Dijkstra, "Please don't fall into the trap of believing that I, Dijkstra, am terribly dogmatical about goto statements. I have the uncomfortable feeling that others are making a religion out of it, as if the conceptual problems of programming could be solved by a single trick, a simple form of coding discipline." Knuth asked Hoare for a definition of structured programming. Hoare gives this definition: the systematic use of abstraction to control a mass of detail and also a means of documentation which aids program design. Knuth himself observes we should be able to define structured programming without referring to goto statements at all. Unfortunately, Structured programming has become a catchphrase whose meaning is rarely understood in the same way by different people. He quotes McCracken, who says, "Few people would venture a definition of structured programming. In fact, it is not clear that there exists a simple definition as yet." Motivated by Knuth's paper, we did some experiments with the Linux kernel, which is a gold mine of go-to examples. Our study of go-to examples in Linux revealed some intriguing patterns. I wrote a note to Knuth to share our thoughts on structured versus unstructured programming. At that time, I did not have the algebra to discern the patterns. Knuth was kind enough to read my half-baked ideas and replied back with an encouraging note, along with a photo of Ramanujan. Let us now look at structured versus unstructured programs through the lens of algebra. Here we have the control flow of an unstructured program. The structuredness is violated in multiple ways. There are loops with multiple entries, an if statement with multiple entries, also crisscrossing between true and false branches of the if statement. Let us apply algebra to compute the compact representation of execution behaviors and find out if it is really difficult to verify L followed by U for this code which looks like spaghetti code. So we have the successor elements and the equations. By solving the equations, we get the CRS. We map the CRS to CRB. Part of the CRB reveals a problem that the loop can terminate with L not followed by U. We can get the relevant behaviors by applying the homomorphism. Here we have the result of the reduced algebraic expression obtained by applying the homomorphism. It shows 4 behaviors inside a loop, and of which 2 behaviors are vulnerable execution behaviors. For example, let's look at behavior 3. We have A2 followed by L followed by A5 followed by A6, then A1 and E. So we have a lock which is not followed by unlock. While it looks like spaghetti, the algebra does not seem to mind the unstructured code. Through the lens of algebra, the spaghetti looks like structured code. The CRS and CRB are similar to what we have seen for structured code. The homomorphism works without a hitch. The property whether L is followed by U can be checked just as easily. This raises a question. While it is ugly in appearance, is unstructured code really different from structured code? The algebra helps us get a good answer for this question. Let us examine the CRS. Algebra shows us that the only differentiation is the repetition of successor elements. We have here the repetition counts for various successor elements. We can characterize the unstructuredness by repetition count of successor elements in CRS. The higher the count, the worse the unstructuredness. To transform a structured program, the program segments with repetition counts need to be duplicated. In retrospect, this provides the mathematical foundation for the transforms in Aston and Zormana's book on unstructured programs. Let us now illustrate the algebraic differentiation of structured versus unstructured. We'll go through some examples systematically. First, we have an example of an unstructured program without a loop. We have an if statement with two entries, A3 and A4. Next, we have a loop A2, A3, A4 with two entries, A2 and A3. We make the loop even more unstructured by introducing more entries into the loop. So we have a loop with three entries. For the first example, E6 repeats twice. For the second example, loop with two entries, E4 and E5 repeat twice in CRS. When we make the program even more unstructured, we have E5 repeats thrice in CRS. Now let's compare the unstructured versus structured version. The structured version is obtained by duplicating some code segments which correspond to successor elements that are repeated. So for example, E6 repeats twice in CRS here. Here we have a replica of E6, E6 prime. Otherwise, the two CRS look exactly the same. The only difference is here we have E6 and that repetition is now replaced by a replica E6 prime. Observe the same thing here. E4 and E5 repeat twice in CRS. In the structured version, E4 prime the replica of E4 and E5 prime the replica of E5. The CRS again look exactly the same except we have replicas of E4 and E5 to avoid repetition. Now here we have a loop with three entries. E4 repeats twice, E5 repeats thrice. So we have one replica of E4, E4 prime, and we have two replicas E5 prime in E5 double prime. Again, the CRS look exactly the same except the replicas So the insights from CRS for structured versus unstructured programming. Whether it is structured or not, CRS is a compact representation of execution behaviors. The complexity of computing CRS does not change. It is n log n. Repetitions of successor elements in CRS reveal the unstructured code. Unstructured code can be converted to structured code by duplicating the code parts for each successor element that repeats. The successor element that repeats k times require k duplications in structured code. The unstructured and structured versions have exactly the same CRS, except instead of k repetitions of a successor element, we have replicas of these successor elements to avoid the repetition. So the distinction structured versus unstructured is delusional. A comparison of unstructured versus structured programs, the CRS are identical. The execution behaviors remain the same. The time complexity of computing CRS remains the same. The difficulty of verifying safety or security properties remains the same. The structured program is likely to be more difficult to maintain because of the code duplication. Structuredness, like indentation, appears to be an affordance for humans. Structuredness is of no consequence to algebra. If humans use algebra, the difficulties posed by non-structuredness can go away. Following the new morality of structuredness advocated by Knuth, we can be better off with unstructured but compact code which avoids duplication. Linux has several instances of such unstructured code.